Welcome to the final project presentation for Engineering 856. My name is Hamid Mahmoudi. I'm the instructor for the course. I'm going to first explain briefly about the project, and then it's followed by a student presentation. The project in this course was the design of a carry look-ahead adder 74283 benchmark using a spin transfer torque lookup table in 10 nanometer FINFET CMOS. What the spin transfer torque provides us is ability to implement a non-volatile lookup tables. So we use the lookup table-based implementation of logic circuits in order to realize combination of circuits. And that basically is by programming the content of a given lookup table. We map the truth table of the desired function into it and therefore realize the function. So this is the way we are going to use spin transfer torque technology for logic implementation. And the spin transfer torque based lookup table therefore is similar to a standard lookup table, except that the storage cells are non-volatile magnetic tunnel junctions. So here, for example, for an n input lookup table, we need 2 to the power of n magnetic tunnel junctions and a multiplexer that selects a unique MTJ based on the inputs, and then the read and write circuit for read or write operation to or from the selected MTJ. So that's the concept of the spin transfer torque based lookup table. At high level, we need to map the gate level design into these lookup tables. An example is shown here where we could come up with different ways of mapping multiple logic gates into a lookup table. And this is the approach that we take for mapping the gate level of the adder into using 2 lookup tables. So this is the schematic of the adder that we intend to implement as in this course as a project. It's a carry look. It's a 4-bit carry look ahead adder, which does carry look ahead in order to speed up the carry computation. The gate level netlist and the Verilog code is provided. And then the students need to do a lookup table mapping of the given design in order to implement that using a spin transfer torque-based logic. This could be done manually or in automated way using LUT mapping software tools. Once the LUT mapping is done, then the LUT mapping needs to be expressed in terms of a SPICE netlist for circuit simulation. So we have sub-circuits of these lookup tables developed already, including the transistors, the FINFET transistors, as well as the magnetic tunnel junction devices built in. And then students can describe the sub-circuit instantiation of the lookup tables they need based on the netlist that they have come up with. For example, here we can see 2 gates mapped to 2 lookup tables, 2 inputs that can be expressed in a SPICE netlist format. And the content of the lookup table, according to the desired function, that can be expressed using specifying the mean terms that are 1. Okay, the collapsing of multiple gates into a single lookup table is also possible, as shown here. You could have group of gates that are single fan out mapped to a single lookup table, and that way you can attempt to reduce area or do optimization. Standalone inverters can be described as a standalone component, but it's encouraged to map them to lookup tables if possible. Like if they're at an input to a gate, then the inverter could be also mapped to a lookup table of the same gate rather than being described as an independent gate. But we have the option of, except for the inverter, the rest of the gates have to be mapped to the lookup table. So here's an example of the SPICE netlist that is provided to students as a template. It includes the model files for 10 nanometer FINFET, all the sub-circuits of the lookup tables are already provided, containing the transistor level netlist and the magnetic tunnel junction devices. And the rest of the netlist is to basically describe the lookup table mapping. And then at the end, we have some descriptions of the vectors to be applied, a test vector for functional verification and also for characterization of power and delay, and some power measurement statements and simulation statements. And these netlists are run by HSPI software tools on a server. And then after running, you can view the waveforms to check the functionality. We have also developed a script that can basically run this netlist automatically for finding minimum delay. The verification also is done automatically by the HSPI. It reports the mismatch inside a file called .err0. So right now, because the netlist is incomplete, there are lots of errors, but the goal is to get no error indicating that the functionality is correct. And then there is a period parameter in the netlist that can be reduced in order to find the minimum possible delay for the design. And we have developed also a script that allows us to automatically search for the minimum period. Another metric of characterization is the area of the design, which is measured by the number of pins for transistors or FINFET. So the number of pins used in each of the lookup tables is already known, provided, and then basically the total number of pins of the design is the sum of the number of pins of all the LUTs used in the design. That's used as another metric. So the project is done in a competitive format where competition is on achieving minimum result in terms of either of the following metrics: delay, the delay of the design, active power consumption, standby power consumption, and then power delay product and area. So students can do their best to achieve minimum in any of these metrics, and they to become a winning project. And to motivate the students to try to win a project, the bonus is that if you are winning in the project in any category, you get 10% extra points towards the project grade, and also that's a good achievement to put on your resume.
Thank you, Professor. So for this project, I had few circuits to try out and optimize based on the different mapping. This is the first case which Professor just showed us. This is schematic on your left. The left figure shows the mapping of we try to make the mapping of the maximum fan-in LUTs, because for MUX sub-circuit STT-LUT, the delay between the higher fan-in and lower fan-in are not that different. And just for sake of comparison, I didn't map any, I didn't collapse any gates on your, as shown in the figure on the right. And I just kept all the gates as their own number of inputs as STT-LUTs.
So back to the case number one. What
yes.
about the case that are not highlighted? How did you
These are the same LUTs, but the same fanning. I didn't collapse any of them. Just the same similar in this case, from this similar as the figure case 1B. The other gate. Yeah. So let's say for this one, this is LUT 5. This is LUT 1. This is LUT 2, 3, and so on. So this is another circuit that I try to optimize based on the different mappings. Because again, like the delay between the higher fanning and lower fanning is not that different in MUX subcircuit. I try to give the higher fanning more, and the other gates are left as their own number of fanning as LUTs. And just for just comparison, I didn't collapse any gates and kept all the gates as their own number of fanning. And I also tried the VTR method, and this is the schematic that I got from the VTR, and with this FPGA structure, and I used the behavior variable code, not the structure. That was the key point in this in this way. So I tried two STT-LUT styles. This is the MUX on your left, and this is this figure shows the static STT-LUT, complementary MUX latch-based LUT, which is provided by professor in this project. And I tried this method as well. This is dynamic. This is called DDR latch-based LUT. And this is a comparison, performance comparison between these two styles in terms of power and delay. You can see it in the power of the complementary latch-based LUT is much higher than DDR latch-based, which is the blue one right here. And also as for delay performance, again, DDR latch-based LUT has a much lower delay as well compared to complementary latch-based LUT. So we expect to have better performance in the DDR latch-based LUT. But we can optimize the delay in the dynamic LUT, which was the DDR latch-based LUT further, because in this circuit, in the figure on the right, this circuit operates in two phases: pre-charge phase and evaluation. So in the pre-charge phase, the clock is 0, and the VDD and the output Z and Z bar, they will be pre-charged to VDD. And when the clock is high, it goes to evaluation mode, and the outputs they started to be evaluated based on the circuit that we have here. So the outputs can be pre-charged to VDD much quicker than the half the clock cycle that we have normally in the circuit. So I tried to reduce the pre-charge time by changing the clock signal as shown here on the figure on the left. Because ultimately this pre-charge time will add up to the delay of the circuit. And this is the real-time clock that I gave to the circuit. You can see almost the pre-charge time is almost is very small. It's around picorange. So you can see that this little drop here. This is the magnetization of that pre-charge time, which is for this case, this is 38 picoseconds. So to summarize, I have 6 different circuits, and I have 2 different LUT styles, and I combined each of them separately and to see which one gives the best performance. And this is the result I got. For that, I got the best delay from case 3, which was the VTR method with the latch-based DDR LUTs. I got 38 picosecond minimum delay, and I got PDP at the minimum delay of 7.9 femtojoules right here. And for active power at the minimum period or minimum delay, I got 169.8 from case 2B with the MUX STT-LUTs and the area of 2796 number of fannings. And I got active power at 2 nanosecond period from case 2B with a latch-based DDR LUT with a value of 75.64 microwatts, and the SAMU power was minimum in this case as well, and area as well in the case 2B. So to summarize, the trade-off between the static and dynamic STT-LUTs is shown here. The trade-off is that the static STT-LUTs are very simple to implement and very easy to design, and we don't have a clock here, because this is static based. But this dynamic STT-LUTs, which is the DDR latch-based, and as shown in the figure on the right. This is more complex to implement to the design because we have to implement the clock as well, and we have the pre-charge time to deal with. But ultimately, it gives a better performance in terms of power delay and power delay products, and so on. So and this is my result. Do you have any questions?
Good evening, everyone. This is our project designing of a adder using a hybrid of 10 nanometer FinFET CMOS and STT-RAM. This is our project outline. Basically, we have realized the adder using the manual method and the VTR, Verilog to routing tool, and of course using ABC synthesizer. And first of all, we have to know why we are using a FinFET instead of the regular CMOS. FinFET is nothing but the adoption of CMOS in the nanoscale. When we go into the nanoscale, that is below 32 nanometer, we will have the scaling issues for CMOS, and that's why we are going for FinFET. And FinFET switching has some advantages over CMOS, like switching speed, etc. And why STT-RAM instead of SRAM? STT-RAM is basically replacing the SRAM nowadays. Because SRAM is occupying more of 50 to 80% of die area, and SRAM has a better performance of DRAM and CRAM. It has low latency, and it leverages the existing CMOS manufacturing process. Now my friend Praveen will continue on how we actually divided the gate level design into LUTs.
Good evening, everyone. My name is Praveen Kumar, and I'm going to explain about the techniques we have used to map LUTs manually. And my team member Sarita will explain about our success story in using ABC synthesizer tool and the results. Basically, we did manual mapping in 4 stages. The first stage, we have used more number of 5 and 6 input LUTs, which resulted in more area, and also due to high fan in and fan out, we got more active power, which you can see here. In the second stage, we avoided 6 input LUTs, which has not only given better area and have also given less active power. There wasn't significant difference in other parameters. In the third stage, to reduce delay, active power and area, we have used mostly 2 and 3 input LUTs, which has shown significant reduction in all these parameters. Finally, after careful consideration of all the parameters and techniques, we have focused more on the intermediate nodes, and we could successfully avoid gates which are redundant. This has shown great results, I would say the best results with manual mapping. Let's see how we got these results. Number 1, we have used mostly 2 input and 3 input LUTs. And number 2, inputs which are common to more than one LUT are efficiently used here by taking output from the previous LUT. This method has helped to reduce the number of LUTs in the critical path, which resulted in less delay. You can see the netlist of S0 and S1 in this slide. We have used only 2 input LUTs. We have used both 2 and 3 input LUTs for S2, whereas for S3 we have used a new technique which resulted in best results with manual mapping, as I said before. For example, gate number 18 has 3 inputs, which are N6, N1 and N4. Gate number 23 has 2 inputs, N1 and N4. So the common inputs for these two gates are N1 and N4. Here we have given output of 23 as input to gate number 18. By doing this, we have reduced the number of inputs from 3 to 2 for gate 18. This has resulted in low area, less delay, and less active power. Similarly, if you take gate number 19 and 24, gate number 19 has 4 inputs and gate number 24 has 3 inputs. So the common inputs in this case are N0, N2 and N6. So output of N24 is given as input to gate 19. By doing this, we reduced 4 input LUT to 2 input LUT for gate 19. Similarly, we have identified gates which have common inputs and have applied this technique effectively, which resulted in best results with manual mapping of LUTs. The final waveform of ripple carry adder using manual mapping is shown in the slide. Now, my team member Ms. Sarita will explain how we got excellent results using ABC synthesizer tool. Thank you.
Hello everyone. Actually, our motivation is to done by the manual way of mapping. Then we were introduced by the tools. Then we were told us to do the mapping using the ABC tool, which was the tool introduced by the UC Berkeley. So I'll just go over the process of installing and how the steps to proceed further for the synthesizing. Then I use the following links for the download and the installation. If you start installing onto the Linux server, you encounter some problems. If you do the make file, then you get some errors. If you get errors, then you are on the right path to go. Then you have some file for troubleshooting. Then we did troubleshooting for that. Then we finally install the ABC on our Linux server. Then once we done with the ABC tool, we have used structural Verilog code to generate the bliss file using VTR through EDA Playground. Why we use structural Verilog code here is the behavioral code is may not be the best choice for if you are aiming to optimize the delay. So we use the structural Verilog code, and the behavioral code has some disadvantages that the carry look ahead of adder property is lost when we go for a behavioral Verilog model. So the main advantage to go for structural Verilog code is the property is not the adder property is not lost. Then these are the steps to synthesize. Then we get the code which is the professor sent us Verilog code. Then we convert the Verilog code to bliss file using a VDA Playground. Then the bliss file, I'm sorry. Yeah. We use the bliss file in ABC synthesizer to generate the optimized bliss file using a below steps. Once we generate the bliss file, you read the bliss file using the command read adder 74283. Then you need to read the LUT library. The libraries which professor has provided to us. Then we need to read the LUT library using the command read underscore LUT underscore lib.txt. That is my file name. Then we need to use the command strat. This is the main command we need to use to transform the network to AIG, that is AND inverter graph. And then for further optimizing, I use rewrite, refactor, and balance. And these three commands, it is experimentally shown that there is a substantially reduces the AAG size, hence the delay. Actually, this was the tool I downloaded directly from the UC Berkeley website. So the FPGA command is not working on this tool. So we use if command instead of FPGA, which is the advanced version of FPGA command. Then what this if command does is, this command maps the currently selected LUT library for the current network. Then we need to write the blip file using a command write adder.blip. Then convert the blip file using the script given by the processor. Run the .st file using the Python script for better results. It is actually minimizing everything, not just best, but it is doing in terms of power, area, delays. So if you observe the netlist here, there are only few number of LUTs, only 11 number of LUTs of different combinations. So the tagline is, if you use the less LUT, the better the results will be. So this is the results we got for using the ABC tool. This with the custom CMOS with no LUT. That was the mapping to LUTs using ABC tool. We got 41 picoseconds. That was the best delay. And PDP is 7.9 farad joule. Yeah. Then area is 2476. So when compared to CMOS, CMOS has a better options. I don't know why we are going for mapping of LUTs to ABC tool. So I had a question initially from the beginning of this project. So I wanted to put it this way.
Right. Yes. That's a good argument here. Why do we go for the first table method?
Yeah.
Practically, one is for reconfigurability of it. They're being reconfigured.
Okay.
They're just trying to minimize the overhead for the other benefits that reconfigurable offers, such as reconfigurability.
Okay.
And practically, we may not do it like the way we are doing this here in the sense that we apply it everywhere. We may do it selectively on a certain number of blocks or components that reconfigurability will provide advantage. So, but yeah, good thought why we're doing it, given that.
Yeah, so many. Yes.
It's due to the benefits that reconfigurability offers.
Okay.
And it will be used on a selective basis on virtually everywhere.
Okay. Then if you compare with the custom CMOS, we were almost there. Our delay is 1.64 times higher than the custom CMOS. Then the rest parameters goes like 15.59. That was the power at 2 nanosecond period, and the active power is like quite large, 3.8 times of the custom CMOS what we can achieve with the custom CMOS. And the rest parameters, I don't know about the area of custom CMOS, so I kept it blank. So the conclusion here is, by using the tools, we can save a lot of time. The tools are not bored of doing the iterations so many times as we are like humans. So that's the best way we can say. We have worked on for manual mapping, which took us a couple of days to figure out which design is the best. But the tools, we spent only 5 hours of time and achieved the best delay, 41 picoseconds. So that's the greatest advantage the tools have. Then we also observed that there are less glitches in the adder waveform when compared to manually. So that is also the observation we did. Then our conclusion is tools are excellent for optimization in terms of power, delay, and everything, and the time saving and if the circuit complexity grows, then the tools are the best best one to use.
On behalf of my team, I would like to thank Professor Dr. Hamid Mahmoodi for giving us this exciting project, which has helped us to learn in depth about LUT mapping and implementing ABC synthesizer tool to map LUTs automatically, and HSpice tool, and also Perl scripting. Overall, it's an exciting emotional experience we had throughout the project. And we would like to thank Professor for the excellent guidance and the valuable inputs you have given us from time to time. Thank you.
Hello and welcome everyone for our final project presentation of this circuit, nanoscale circuit and system course. I would like to thank everyone for this wonderful experience of learning. We have all learned something new in this course, and I would like to thank all my fellow classmates and esteemed professor. In our project, we all have to work with the same design. So I will not bore you with all the explanation because it's not something different. But for someone who would like to explore the idea, so we put some background of our project as well as some theoretical and physics of the STT ramp and our design of the FINFET device and how they work and interact. But I'll directly like to go to our methodology and I'll explain what we have done in our project. So before we started our project, we'd like to look into different aspects, how we can attack the problem to solve our the situation of getting a better result. For optimizing methodology, we have considered the manual LUT mapping, and also we have considered the software-based synthesizing model, where we have considered both behavioral model and structural model. While we tried to do the manual LUT mapping, unfortunately, it was not giving us very good results. The results were very primitive. It was tedious and error-prone. So we thought, okay, we should basically depend on the output that we are getting from our software synthesizers tools. So so for that, we have used our behavioral model and structural model. I'd like to note that when you use structural model, we are supposed to get better delay. And when we use behavioral model, that is supposed to give us better power. But we got some interesting results. So I would like to explore that even more further. Now my group mate will explain the rest of the part. Thank you very much.
Hello everyone. We use VCR and ABC, and we specially use for these three simulation, and 50% of them were successful. These are our results. Because we have two structural models here and one behavior model, and for active power, the best result that we got is in at 2 nanoseconds is 39 and microwatt, and for standby power, our best result is 37 nanowatts, and our best area is 1360. And our best CDT is 23.31. Yes, actually, we did different simulation with VCR and ABC synthesizer, and we have our netlist here. That's Anil covered.
So, sorry about it, standard power is actually microwatt and not nanowatt. So, I just want to check that. Okay, so for the structural model, these are actually the netlist which we have used here. So in ABC, after synthesizing with PCR, we use ABC to optimize our netlist even more. We use the Renode, DSD, and cleanup command to optimize our design. And this is the netlist which we got, and we have 8 LUT3. So with which we got our area to be 1360, which is significantly low according to us. And the structure 2 model, which we have used the netlist for that is this one, in which there are 1 LUT2, 4 LUT4, 2 LUT, 1 LUT4, and 2 LUT5. And for this, we have used FX, DSD, and S-trash. So, yeah. So with this, we get our lowest PDP according to our simulation, which we have done. And this is a behavioral model which we did, but that didn't give any significant results.
And one more thing that we have only considered the static LUT mapping. So we could not really use the sequential synthesis because for that we needed a clock cycle. So we only considered the static LUT mapping and got all the results on the basis of our static LUT mapping. And also it is very interesting when we were trying different combinations, if you change the sequence of the combination, it gives different results. Sometimes we'll use one combination that will give us some error, but if we just change the combination, it gives us different results. So we believe if we explore the comments and if we try to understand how those comments individually affect the whole design, we can even further optimize our design. Thank you. Actually, when we were reading the comment in the ABC synthesizing tool, each comment kind of explains what that does. Depending on that, for example, for this one, our structural model 1, we use the comment cleanup, DSD, and can you please go back? Yes, cleanup, DSD, and Renode. So what cleanup does, it eliminates the dangling node. So if there is any dangling node, it cleans that up. Also, the Renode will reconnect the nodes. So and DSD also. So all this kind of only aids the area. So while we were trying different comment, what we tried to actually, because we were not giving very good delay. So what we tried to do, we tried to accumulate some comment that will give us better area. So we try to use those that will aid the same type of problem. It will attack the same type of problem and give us a better result instead of having 2 different comments working on optimizing different ideas. So that is what we basically did because we did not have any other option rather than going for trial and error method in the comments. Thank you very much.
All right. Very good evening, everyone. My name is Puneet Chaudhary, and these are my partners, Bayo and Harshit. So this is our project, design and characterization of orbit array using hybrid of 10 nanometer FinFET CMOS and STT-LUT. So like when we got to know about this project, we have tried like a lot of LUT mapping techniques like manual mapping and several tools, synthesis tools. So we'll discuss it further later on. So these are our overview. Like we have tried like a lot of designs using several types of tools, and we like worked out on our outcome. And our main focus was on like the delay and the PDP and area. So these are like our main concern, like to how much optimized we can get all of these parameters. So we have tried like almost 7 to 8 designs using manual mapping and tools, which we will discuss further later. And these are some of the designs we use, like design 1, design 2, design 3, design 4, design 5, and design 6. This is the active power and this is the standby power. And further on, I would like to call Bayo to discuss about these designs and the method we used for these designs.
So we had to talk about the various conventions of naming the design. That was one. Thank you. So we had to talk about various conventions of naming our designs, and then, so we call design 1. We use Xilinx tool for design 1, and then in design 1 we had two LUT3s and 4 LUT5s. For design 2, we just use the manual method, and then in design 2 you can see we had 6 inverters, 21 LUT2s, 5 LUT3s, 3 LUT4s, and 2 LUT5s, and so on. For design 3, we use the ABC tool, and then we just, kind of latched onto Xilinx. So for the total utilization for the area, we had to make the multiplications by the number of fins based on what was given in the material. So you can see that design 1 gave us the total area 3164. Design 2 gave us 4950. Design 3 5090. Design 4 5202. Design 5 3870. Design 6 we had 3870 as well. I mean, they were pretty much, design 5 and design 6 used the same LUTs, but the layout was kind of different. Sorry. So this is the schematic for design 1. So the way that we call this design, we just say adder. So we would say adder 5 5 5 3 5 3. That way we knew what was going on. So this was the schematic for design 1. And then for design 2, we had to go back and do the manual thing because we were having little challenges. So we had to go back and be sure that we knew what we were doing. And then when we were convinced, so we had to go back and then use the tool. So we had to use, for the design 2, we had to do the manual thing. Then for design 5 and 6, we had to go back to Xilinx and then optimize. So this is the schematic for design 4. And I will hand over to Harshit.
This is a simulation result for the design 5 and design 6. And over here we have the inputs for the adder like A and B and the carry in, and the output is carry out. And from the simulation we can get like whatever the design we gave to the H5, it gave the correct result even after the delay, whatever the delay is. Even if we minimize the delay or area is moved, we get the correct result. So for every design we do simulation, and this was the best design, that's 5 and 6. So this is the design, like we have 6 designs. The design 1 that has 79 picosecond delay, which is like the first design which we have, because the Python script which is given to us has 100 picosecond which over there which fails. Then after editing that we got 79. For the second one we got 133. Third one is the ABC. I don't know why it's like after running that from the ABC tool we got infinite delay. And from the fourth one we got something around 133, and the fifth and the sixth are 30 picoseconds, which we got after the minimization and the optimization of the design. So 30 is the best design delay which we got. But in the 5 and the design 6, what's the difference? If you go back, So the best design which we have 5 and 6, only the layout changes, but the number of LUTs are same in the design 5 and 6, where we got the 30 picosecond delay. And so for the 30 picosecond, we got 11.7 is the PDP and the area is 3164. Standby power still we have to calculate, we haven't calculated yet. And the active power is 391. And at 2000 picosecond, the active power is 109 and PDP is 218 and area is 3164 again because the LUTs are same.
Good evening, everyone. We have four manual mapping designs. So the 3 manual mapping designs and one design is with VTR. So this is the design 1, which we use automatic mapping. So in this we have 2 LUT4s and 2 LUT6 and 2 LUT5 and 1 LUT3. So the minimum which we got with the VTR is 184 picoseconds.
5 LUT5. As you can see, the colors are representing the actual areas on the outer circuit of the gates. So as we mapped this manually, we had different combinations, but this is just one of the combinations we did. And the results we got from this combination is, after minimum, we had a minimum period of 184 picoseconds and power.
We've got at the test has paused at 93 picoseconds. Yeah, at 93 picoseconds, but we are getting power. We are getting more power, and the value is very high. So if you see at 125 picoseconds, it is also passing the test, but the power is low, and it's like incomparable to with at 125 and 93, and in this is another random manual mapping we did, design 4, and here the Python script is still running, so we'll update the result of this.